Good morning, or afternoon, actually, good afternoon.
Hello, everybody.
So just seeing what review I had done for test 4 in the mini lectures here. I'm not starting yet, don't panic. Well, that's not very nice, is it? Annoying. Annoying as all get out. Okay. All right, folks, we'll get started here. I was going to start on review. Did anybody have any questions before I get started about test 4?
Oh, what day is test 4? Because on the syllabus it says the 27th, but I wasn't sure if it was actually this week instead.
No, it's the 27th.
Thank you.
Why, Anna, did you have a reason for thinking it might be this week?
For whatever reason, last week I thought today was the review session, so that's why I was a little bit confused.
Oh, okay. All right. Well, anyway, yeah, so it's next week, next Tuesday. All right. Any other questions before we get started here? All right. Well, something's up with my version of Word, probably because it's from 2008. Probably has something to do with it. But anyways, I'll make the best of it. It seems to be shrinking my structures for some reason. I'm not sure why. Okay, so this one here is a Novenago condensation. I'm not going to go through the mechanism of it. If you want to see the mechanism, you can look at the key. But the main, well, I'll show you how you can get the answer fairly easily, as long as you recognize it's a Novenago. The Novenago has a very similar kind of pattern to the aldol condensation. So what characterizes it as a Novenago is the fact you've got this dicarbonyl compound and an aldehyde or ketone being reacted with it along with a base over here. So the pattern is fairly easy to come up with. It's the alpha hydrogens that are going to be lost along with the double bond oxygen. That becomes a double bond. Then your only decision has to be, well, do you include squigglies or not? And in this case, you don't, because the top part is going to be symmetric. So it's the bottom part too, actually, as it turns out. Anyway, that would be the answer there. Anybody have any questions? Okay. Like I said, something's up with my version of Word here, so bear with me a little bit. This one here is a Claisen condensation. Again, I'm not going to do the mechanism for this. You can, if you want to look at the mechanism, you can always look at the key. Now the thing is that even though there's not a 2 out the front here, because it's only one ester and it is a Claisen, you know that it's going to be reacting with itself. Well, you know, another molecule of itself. You've got to realize that when you've got a bottle of this, it don't have just one molecule of it. Nobody could ever isolate one molecule of anything. So there's going to be presumably a whole lot more. So I don't really need a 2 in front to denote that there's 2 of them. You know, some people are looking at that saying, yeah, that seems a bit unfair, but you know, well, that's how it is. Actually, I'll do this. So the join is always from the alpha carbon of one to the C double bond O of the other, with the loss of the ester grouping in a hydrogen. So the product of this is going to be this compound here. Does anybody have any questions? Nobody has any questions? Okay. All right, this one here is, oh, by the way, I do have in the mini lectures another test review. So if you want to take a look at that, you can. It's in spring, I think it's spring 2019 is the one I've done in that video. It's in the mini lectures folder if you want to take a look at it. Okay, so this one is a 1,4 addition because it's got the copper lithium compound. And the product, let's see, it's 1, 2, 3, 4, 5. Sorry, hang on. 1, 2, 3, 4, 5. So that would be the answer there. With the copper lithium, you've got to remember that only one of these is used. Even though there's 2 here, only one of them gets used. And the attack occurs specifically at this carbon right here. Does anybody have any questions? I'm not going to do any polling for this because I imagine that most of you haven't even looked at anything yet. I've got to be realistic. through all my years of teaching, I've come to realize that. So for this one, we've got, well, I recommend putting it in Pac-Man style, like I've been doing. So that involves flipping this around. So this is one that just requires a 2D diagram because the double bond compound, the diene here, is not joined up inside a ring. All right, so that gives us a 6-membered ring, and we have to preserve the stereochemistry as well, which means I have to show the stereochemistry here because it's a trans alkene. It ends up being trans in the ring here. And that'll be the product for the Diels-Alder there. Does anybody have any questions? Does anybody have any questions?
So you didn't want the 3D view with the chair? You could just do that?
Yeah, because because it's not one of those that requires it, Jasmine.
Okay, I just watched the video.
And no, it's only if this is part of a ring, inside a ring, that's the only time you have to do the 3D diagram.
No, okay, I got you. So you still do it anyway when the, okay, I got it.
Okay, but you still need to show the stereochemistry regardless. All right, so for this one, this is a addition of a alkyl group into the, doesn't matter which side you put it on because this one's symmetric, but there'll be 3 carbons there because that's what's going on with that one. Does anybody have any questions about that one? Enamine assisted addition, I think it's called. So. All right. So for this one, this is an asymmetric ketone, alpha addition to an asymmetric ketone. And because it's ET3N and heat, it's going to go on the more substituted side. So it's going to look like this. Let's see, 1, 2, 3. Yeah, okay, there you go. So that's what it would look like with a double bond here, obviously. Any question? Okay. And this one here is a Michael addition or Michael reaction. And the product is going to be...
Can I ask a question?
Yeah.
How could you tell again that it's a Michael addition?
Because one of the reactants is this alpha beta unsaturated carbonyl compound. And it could be switched, Julie. I mean, you know, this could be out the front and this could be on the arrow. It doesn't really matter. But that's the main thing, is that it's an alpha beta unsaturated a ketone or ester in this case, and that's a nucleophile that's being added there. So it goes here on what amounts to the beta carbon. That's where the nucleophile adds. Is that what confused you, Julie? Is the fact that it's on the arrow and not in front?
I just don't, I guess I don't really, I mean, I do know what an alpha, beta, whatever it is, but it's too long a word for me. I can't remember it when I see it. Like I look at it and I'm like, yeah, well, that looks like an ester.
Well, yeah, what you're looking for is this.
So it doesn't have to be an ester. It could be
No, it could be anything.
anything with two.
Well, it's going to have a CC double bond in conjugation with the C double bond O.
Okay.
All right?
Okay, thank you.
That's what you're looking for. All right, any other questions?
Well, I have a question.
Mhm.
I know more than likely I'll do this on the test. So the alpha and beta side, what happens if it's flipped? So instead of the beta side being on the phenyl side, what if it's on the OME side? Like it's flipped around.
It wouldn't make any difference, I don't think, if I'm getting your question correctly. I mean, what you're suggesting is this, or I think. Yes or not? Because that's what you're asking. I mean, if it's flipped around, well, the answer is it will connect here.
Oh no, I was meaning for the final product. So you have it being added to where the negative is. So instead of having the
Oh, you're saying could this OME be over here and the pH be over here?
yeah.
Yeah, because that's a single bond. There's free rotation about that single bond.
Okay, that's what I just wanted to make sure. Thank you.
Yeah, no, that will work. All right, any other questions? Okay, this one we can see, which is good. This is the one that requires 3D, Jasmine, because the diene is part of a ring.
Yeah, I was just confused. I thought you didn't want us to show it at all. I was like, wait, that doesn't, no, I was just goofing off. Sorry.
I think I might have done this one before, but I'm going to do it again anyway, just for kicks. Oh, sorry. All right, so this arrow here, I guess I could draw it probably a little bit better. Maybe just kind of draw it like that. But the C's that are going to join together, these black C's here. Now I'm going to show this as a 2D first, and then I'll show what the 3D looks like. Like I said, a lot of people don't like doing the 3D diagram. They convince themselves that they can't do it, so they don't. Okay, so this is the 2D diagram here, along with the stereochemistry, since it's a cis double bond essentially. There you go. Does anybody have any questions? so far? Now that's not going to be a suitable answer. You need to do a 3D diagram for the test. So what I suggest you do is for the, let me see, I'll put my colors in here. It's clover compound, it's a clover color. So for the actual carbons that were involved in the Diels-Alder process, that's a 6-membered ring that can be drawn like this, kind of like a closed, or, you know, one of those, a book that's fallen on the floor and it's kind of tented like that. And then what you can do is, after you've done that, you can put in the bridge, which is going to be this business here. And that is going to be forced off to the left or to the right. And then this can either be drawn up or down, but it has to be drawn one of the two.
I have a problem with what you're doing.
You do?
Yeah, because
Is it wrong? I don't think it's wrong.
I don't know.
We have,
I think it looks okay to me.
Okay. I thought that the C's that were connecting it were the second C's in. I guess that still works.
in this case, do we need to show, we still have to show endo and exto though?
No, just one of them. It doesn't matter which.
Okay.
This one would be.
Yeah, you're right.
This one would be endo.
Yeah.
And the exo would be if this was sticking upwards, but this has to be either sticking out to the left or to the right. In this case, I got it sticking out to the right. That would be correct right there.
Thank you.
Does anybody have any questions? Julie, do you still have concerns about this?
I don't know. I guess I got to redraw it a few times.
There's many right ways to redraw it, or many right ways that it can be expressed. Also many wrong ways as well. All right.
That's exactly what I was thinking.
Yeah, I thought you might be.
So on the test, you don't have to draw out both ways. You can just have
No.
one and just label it.
Well, it has to be the 3D.
Well, I know, but I mean, like, if you wanted it upward or
No,
like endo or exo.
no, it's okay. I mean,
Okay.
it's fine. Oops, wrong one.
Okay, I have a question about the bridge.
Okay.
So how do I know when I'm looking at it that the bridge, both parts of the bridge aren't on one plane?
Because it's not double bonded, Julie. Since it's a single bond right here, it means it has to point either to the left or to the right. If that was a double bond, yes, they'd be in the same plane. Because double bonds are flat. sp2 hybridized. This is sp3 hybridized.
Okay. Thanks.
Any other questions? Any other questions? All right. Okay. This one here is a crossed aldol. Now, as such, you can express it with a pattern. And this is the one that's going to supply the alpha hydrogens. The other one doesn't have alpha hydrogens. as is the case with these. Now this one is going to need squigglies. Oops. Doesn't matter if the squigglies go on the top or the bottom. Okay. Any questions? Any questions? All right. So this one is an Acetoacetic condensation. Let's see, how many carbons do we have? 1, 2, 3, 4, 5. So 5 in the chain. And the product's going to look like this. And that'll be the final one there. Anybody got any questions? Okay. I think that's it. All right. So with this one, you should expect that you should start out with the actual reactions. And the mechanisms. So that's going to be what I'm calling product A, or pathway A. Both of those are interchangeable, really. The pathway or the product. Product just means the end of it. The pathway just means the entire part of that. And for the other one, yeah, this is resonance. That's why I've got the double-headed arrow in here. And that would be B, and this whole thing you could call pathway B. All right, does anybody have any questions so far? All right, so the energy diagram is going to look like this. You'll have energy on the y-axis and reaction pathway or coordinate, something like that, on the bottom. So it starts out at the reactant, which is what we're starting with, obviously, an HBr. Now, pathway A, I'm going to denote with, let's see, I'll denote that with a dotted line. And pathway B, I'll denote with a solid line. Right, so this is how it's going to look. Now, pathway A is going to look like this. And pathway B is going to look like this. All right, so what we're interested in here is the different bits and pieces. This point is representative of this carbocation. And this one here, oops. Is representative of this carbocation. And down here, this is the A product. And this is the B product. Okay, does anybody have any questions?
For the test, that's exactly how you want it.
It's not about what I want, it's about what's right, Deanna.
Right. I was like referencing to like labeling, like
Oh,
instead
no.
of
If you wanted,
product.
if you wanted to, you could label these with letters, and
Okay.
then put letters on here. I mean, people have done that on old tests as well.
Okie dokie.
All right. Okay, I understand where you're getting at now. Keisha, would you please mute if you don't mind? All right, then we need to get into the explanation as to why these go the way they do. And it's asking for the thermodynamic and kinetic product. Now, the thermodynamic product is this one. And this is because this is a more substituted double bond. So thermodynamics is always about which product is more stable. Okay, so that's I'll say that more stable product. Okay, so it's a more stable product. And the kinetic product is this one. And this here, there's the activation energy is lower. And there's a difference in stability between these. This is the more stable carbocation. No, it's not. Sorry, I'm lying about that. This one's the more stable carbocation. Because it's tertiary. And this one is primary. And that would be enough of an explanation there. All right, so the intermediates, when I'm talking about intermediates, we're talking about these carbocations. And the products, of course, are the things we're getting at the end. So I've incorporated all of that into the answer to the question, which is what was required. But as I was just saying to Deanna, you don't have to label. You can label these with letters or something else, and then, you know, A, B, and C and D, and then put those on the diagram in the correct locations. As long as you're very clear about what's what and why something's more stable than the other, and you know, what represents kinetic and thermodynamic products, I think you're good. Does anybody have any questions about number 2?
Just to clarify, the thermodynamic product is more stable because it is more substituted.
The double bond is more substituted, yes.
The double bond. Let me put that in. Bond.
So if you look at the double bond on the bottom one,
Mhm.
it's got 4 C's connected to it, right?
Mhm. So
How many C's does the top one have?
2?
Connected to the double bond?
Oh, just 2?
Just 2, that's right. So it makes the other one more stable.
Thank you.
All right. Any other questions? Other questions? Okay. That should be a gimme on the test. Most people usually get that right. This is a Claisen condensation. And you're given both the reactants and the products here, so you should be able to come up with a mechanism. Remember, the possibilities for this one could be an aldol, a crossed aldol, a Claisen, or a crossed Claisen. Not sure who it is, but somebody's making a lot of background noise, and I'd like them to mute if they can, please. I think it's really hard to memorize these mechanisms. I think if you understand what the arrows are telling you, it's much easier. I generally can tell who's memorized mechanisms or attempted to versus the people who actually understand what's going on. And believe me, the people who understand what's going on are out there. that would be it. That would be the mechanism there. I suppose we need mirror over here as well. Does anybody have any questions? Any questions? Okay. So this is an acetoacetic ester synthesis, and you can tell whether it's an acetoacetic ester or a malonic ester by looking at this grouping here on the next to the C double bond O. And if it's an OH, it's a carboxylic acid, which means it's malonic ester. Since it's a methyl group, it has to be acetoacetic ester, which means the starting compound is going to be this one. Oops. So that's going to be one of the groupings. It doesn't matter which one you add first. Now, the way I figure this out is just by looking at the alpha carbon on this side and looking at what's attached to it. And I know that that's where the alkyl group is going to be. That alkyl group can be a Br, a Cl, or an I. It doesn't really matter which. All right. Any questions so far? Okay, so the other one is going to look like this.
Could you say again how we know what the second group was?
Just circle this grouping right here. And see this C here, that's the one that's going to have the halogen of it. This one right here I'm pointing to, Julie.
And how do you know that?
Well, it's a nucleophilic process, right? So the negative has to come in and attack this nucleophile like this. Or nucleophile comes in to attack that C like that, which is how you know that negative is going to join on to the C.
No, I mean, how do you know where it's joining on?
Because this is the alpha carbon. That's the one that is most acidic right here. See that? So you're looking, that's that C there is this one here I'm pointing to.
Okay.
Is that okay?
I don't think I could do it again by looking at it, but I don't know. I'll have to figure it out.
Well, let me see if I can help you figure out the problem here. I'll redraw it. I guess I was a little bit lazy, but I'll redraw it here. Okay, so these are the groupings. And the carbons I'm pointing to are the ones where you're going to end up attaching these halogen groups.
Okay.
Is that okay?
Yeah, it's better.
So focus on that carbon right here, the one next to the C double bond O. It obviously isn't the methyl group.
Would it matter which grouping reacts first?
No,
Does it matter?
no, it doesn't matter. All right. Does anybody have any questions? So there's no mechanisms or anything expected for this. But if it helps, then do what I did here and circle the groups attached to that alpha carbon. And then also maybe just notate where you're going to put the halogen group. Okay, does anybody have any questions? As I was intimating earlier, these two can switch. It doesn't matter which one goes first. So question 5. Anybody got any other questions about this one? All right. Now question 5. So what you do is you actually just look down here and you can see how big the ring's going to be. So you know it's going to be a 7-membered ring. Now what I like to do, I'm going to go ahead and do this here. I did this earlier when I went through these. Now from the outset, it should be clear to you that this is not a symmetric diester. Now I like to go ahead and number these as well. So given that it's an 8 chain, you know it's a 7-membered ring, but you also know that from down here as well. So it's going to be 2 ring compounds we're going to get from this. And I'm going to do, first of all, let's see, it'll be 2 to 8. And the other one will be 7 to 1. So it's always the alpha of one to the C double bond O of the other. So when you're doing these, look for the ring size and then just start out with the base structure, which is always going to be C double bond O of 1, and then the ester group of an adjacent one. If you're doing 2 through 8, what that means is the ring is making up 2 through 8, and this will be number 1, which makes this 2, 3, 4, 5, 6, 7, 8. And we have methyl groups at 3 and 5. And the other one here is 7 to 1, which means that the 1, this will be the 7 here, and that'll be the 1, and this will be 8, and then just number in the rest of them. And we have methyl groups again at 3 and 5. So that's A and B, but I don't know which is A and which is B at this point. Does anybody have any questions? Okay. Now the next step involves this is really just like the reaction we were just doing. So this is a methyl group right on the end here. And that's going to be added on both of these, and it gets added here at this point between the two carbonyl groups, because that's the most acidic carbon. So again, methyl groups are in the same place, and this methyl comes off here at the carbon that lies in between the C double bond O groups. Does anybody have any questions? So we do the H trio plus, that will convert the C double bond O OMe compound into a carboxylic acid. Everything else stays the same. You might have not drawn that probably, so 1, 2. It's better. All right. And then the heat will leave us with the final compounds here. I don't like that either. All right, let's see if I can draw this a little bit better. Let's do that. And that gets rid of the carboxylic acid grouping. That's it. That delta means heat, just in case you haven't seen that before. Okay, so that's a delta, not a D, it's a delta. All right. So now I have to look at these two structures at the end and figure out which one matches the one that I have here. And it should be clear that this one, what I have at the end here on the left-hand side, matches this one that's on the left-hand side, which means that the lettering just mirrors what's here. So that would be E, D, which makes this one A. And this would be B, C, F, and G. Does anybody have any questions about number 5?
I was just going to ask at the start, you really don't know until you get to the end which one is going to be the one.
That's right. It's kind of like life. All right, any other questions? But Peter, you know, if you wanted to, I mean, if you were really keen, you could possibly start at the end and work your way backwards, figure it out that way. I don't think that's the best way of doing it, but you could do it that way. I think it's a lot of trouble. I think you'd do it if you just want a little bit of pain. I don't know. All right, any other questions? All right, so I was going through these at the end of the last class, I believe. And my first challenge to you was to determine, well, which one of these is coming from an aldol, which one's coming from a glycine. This one's coming from an aldol because the product is a C double bond C in conjugation with the C double bond O, alpha beta unsaturated carbonyl compound. And what I would encourage you to do here is, well, you know, you've actually got that drawn there. You don't have to redraw it since it's there. I'm going to have to redraw it so I can do it. And what you would do is you split this down the middle, and one of them gets 2 H's and one of them gets a C double bond O. So the C double bond O is going to go on this bottom one, the one that doesn't have the C double bond O to begin with, that's how you know. And the other one gets the 2 hydrogens. Now, if you don't remember the reagents, you can always go back to question 1 and find a reaction that's similar to it. Another aldol reaction. And I'm trying to remember which one is the aldol. Here it is. So NaOH, H2O, and heat, so you can just copy those straight off. So you don't even really have to remember reagents as long as you can. As long as you can do that. Does anybody have any questions? That's for part A. Okay. And part B is the glycine condensation, or specifically a crossed glycine. So the most important carbons are the alpha carbon to the ester grouping and the beta carbon up here. And this is the bond that you kind of switch or you split. So the 2 things that you would have here would be the C double bond O, and then you split the other one off as well. Now the one with the ester grouping gets the hydrogen, and the other gets the same ester grouping as you have on the first ester. And then the reagents, again, you can go back to question 1 and hunt it down, but it has to be the same ester grouping, again, NaOET, ETOH, and 2 H+. And that would be the completed problem there. Does anybody have any questions? All right. Well, you know, it's a fairly predictable test, really. I mean, as far as the kinds of questions you're going to see. So generally, people don't do too badly with it. I mean, the only time people do badly with it is if they don't study, or they wait, or they think that maybe an hour's study is enough to get through it, which it ain't. Does anybody have any other questions about the test at all?
Mostly, what are you going to go over on Thursday?
Well, I can go over another test. I can answer any questions. I'm really hoping that by Thursday, people have done something. But part of the reason I feel like I didn't get any questions today is because nobody's done anything. I shouldn't say that, but I mean, and if I did a poll and asked how many people have actually studied, I think I'd find that not very many people have done anything. I could be wrong. I'm going to do a poll. I'm going to see. I'm going to do a poll. Remember, it's completely anonymous. Let's see. All right. Actually, I'll make it more generic so I can use this one again. Okay, we'll make it 0. So this is hours here, all right? 1, 2, 3. You can round up or down depending upon what you've done. Okay. Okay. All right, let's have a look. I'm ready for whoops. I'm ready to be depressed. We'll see. All right. I'd like everybody to answer, please. Honestly, look, I can't tell. All right, I can't tell anything. All right, but it helps me to know. Got 3 more people to vote. 1 more. Thank you. There you go. All right. Well, look, I owe you an apology then. I thought that the zeros would be more than 5, but yeah, there you go. I'm glad some of you have done some stuff here. Some of you have done a lot of stuff. It's good. All right. Okay. Other questions? Oh, okay. Thank you, Deanna. I appreciate that. All right. Other questions? Any other questions about test 4? Yeah. So I moved my desk in front of the window. So now you can actually see my face. It doesn't look like I'm hidden in the dark, but my desk was in the corner. I don't know if you noticed. A bit different. All right. Any other questions? Because otherwise, I think we might just leave it here, and I'll do another test on Thursday. Just go through that. All right. Well, we'll leave it there then. And if anybody wants to hang around and talk to me, they're more than welcome to do so. Otherwise, I'll see you all on Thursday.
Thank you.
Thank you.
Thank you.
Dr. Musgrave,
Yes, Adrian?
I have a question about the lab, if that's okay.
Yeah, sure. Yeah.
I submitted my reaction kinetics assignment, but I wasn't getting the right value for M,